Welcome to Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be looking at our first set of notes from Chapter 3, which deals with scientific measurement. And because this chapter deals with the types of measurements and how we make them, and the types of math and how we do that math in chemistry, this is really one of the core chapters the entire year. In many ways, it's probably our most important chapter. These ideas get used in most every chapter the entire year. Every time you get out your calculator and do any kind of math in chemistry, you're going to be applying ideas from chapter 3. And understanding some of these ideas related to measurement starts with an understanding of which is bigger, 5 or 120. Now, most people will look at that and say, well, 120 is of course bigger, but it really depends upon the type of units because units give a number meaning. I mean, it could be 5 if it was 5 quarters and 120 pennies, or it could be 120 if it was 5 pennies and 120 quarters. So really, a number without a unit is meaningless in chemistry. Very rarely will we ever see just a number because that unit behind that number is what really gives depth and meaning to that number. Now, the first type of measurement system we're going to talk about here is the English system of units, which was really developed from common use, which is good because people had a need to measure something, so they came up with a way to measure it. Other people ended up copying them, and pretty soon we had an entire system of units derived around the fact that people needed to measure things. The problem with the English system of units, because it really wasn't designed, it was just created out of use, it lacks uniformity, it lacks coherency, and it's really not all that easy to use when you're converting from one type of unit to another. So along came some French scientists, and in 1795, they developed and published the metric system. Now, metric system is very different from the English system of units, and then it was designed from the ground up to be easy to use, to be very uniform and very coherent. And in many ways, this system came about because of the French Revolution. If it weren't for the fact that at this time frame there was a overthrow in France of some of the old governmental powers, and some of the new people stepping in said, hey, we have some scientists that had a great idea. Now we have the power to enforce it. In many ways, that led to the birth of the metric system because now you had a people willing to use it, and from there it ended up spreading. Now, the nice thing about metric is it's simple base units. So they looked at, okay, what types of things do we want to measure? And they said, let's come up with one fundamental unit for each of those types of measurements. And then we're going to have interchangeable prefixes. They understood that sometimes we wanted a long distance or a very, 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 very short distance. And if we just use the same unit all of the time, sometimes you would end up with very large and very small numbers that were cumbersome. So they figured we could make each base unit worth a fraction or a larger part of that unit based upon interchangeable use of prefixes. And it was a decimal 10 system, so conversion is very easy. It's really just multiplying and dividing by 10, which is simple as sliding the decimal. Now, one of the reasons why the metric system is necessary is if you take a look at English weight units. I mean, all of the different types of weight units, which often even share the same name but sometimes mean different things, and all of the goofy conversions between them make for a very, very cumbersome, hard to use, and hard to remember type of system. Well, with metric, we can establish a base unit of length like the meter, and by using prefixes, we can change very simply what that meter actually means. So these are the 6 basic prefixes above or below a base unit that you should have a working knowledge of and recognize. So the largest one we're going to look at here stands for kilo, or I should say it stands for 1,000, and it's pronounced kilo. It has a symbol of K. So 1 kilometer would be 1,000 meters. 1 kilogram would be 1,000 grams. 1 kilosecond would be 1,000 seconds. So we can stick that kilo on the front of any base unit, and we can alter its meaning. Now, if we wanted a very long distance, kilometers would be very, very useful. But let's say we wanted a shorter distance. Maybe hecto might be more convenient and give us a more normal number. Hecto means 100, so 1 hectometer is 100 meters. Next one would be deca. 1 decameter is 10 meters because deca stands for 10. Think of decade, 10 years. Same idea. Now, those are the 10 times bigger, 100 times bigger, 1,000 times bigger than a base unit. Well, what happens if we want a smaller than base unit? Well, that's where decicenta in milli comes in. 10 times smaller than the base unit would be deci. So it literally stands for a tenth. So in 1 meter, there are 10 decimeters because a decimeter is a tenth of a meter. Centa would be a hundredth, so 0.01. So there'd be 100 centimeters in a meter. And milli would be 1,000. So there's 1,000 millimeters in a meter. And once again, these are interchangeable prefixes. We can use these with grams. We can use these with seconds. We can use these with meters. We can use these with liters. We can put it with any interchangeable unit. Now, while there are 6, if you really look at what we use throughout the year in chemistry, we use kilo, we use deci, we use centa, we use milli. We use those 4 more than any of the rest. So if you had to guess which of the 4 I have to memorize and actually know what they mean, those would be the 4. And which of the 4 are most likely to appear somewhere on a test? Probably these 4. Hecta and deca pop up every now and then, but really kilo, deci, centa, milli, we're going to use more than any of the rest. Now, one of the things I want you to be able to do with metric is understand it. And since in many situations we don't really use these units in everyday life, what I want you to do is when you see a certain unit, what do you think of that helps you really remember what it really stands for? Liter's probably the easiest one because you've all had 2-liter bottle of pop. So picture a 2-liter bottle of pop, cut it in half, and that's a good estimation of a liter. Now, when you actually see a cube that really stands for a liter, it's typically a little bit smaller than most people think. And that's because when you see a 2-liter bottle of pop, you're seeing a curved surface with a smaller top and a smaller bottom on it. So honestly, a liter is probably just a tiny bit smaller than you think it is. Another one you probably are familiar with would be the meter, because you've probably seen meter sticks in school. Now, when I was a kid, we used yardsticks. So when metric really became much more prevalent, teachers started having a meter stick rather than a yardstick. Well, how do you know the difference? Well, most of them have both types of measurement systems on them. So if you flip your meter stick over and you see that it has inches on the back side and there's more than 36 of them, then you know what you really have is a yardstick and not a meter stick. So a meter is really just a few inches longer than a yard. Good estimation is to picture the middle of your chest all the way out to your fingertips. If you hold it out at your raise it parallel to the ground and hold it out and stretch as far as you can, that's going to be pretty close to what a meter is, from your fingertips all the way to the center of your chest. Now, parts of a meter. Well, first, decimeter. Now, I used to use cassette tapes to talk about this, but finding a lot of students don't really have cassette tapes anymore. So for a decimeter, picture a large orange. If you can hold your fingers apart between your index finger and your thumb and make a guess, okay, this is what a large orange looks like, well, then you got your decimeter. A centimeter would be the diameter of a shirt button. So if you can picture a button on a shirt, centimeters are going to be pretty close to that. And finally, a millimeter would be about the thickness of a dime. Now, are any of these perfect that we've looked at? No, but that's not really the point. You're trying to get a working knowledge of something. So if on the test I told you, you have a unsharpened pencil, is that going to be closer to 8 meters, 8 decimeters, 8 centimeters, or 8 millimeters? You'd have a working knowledge that, well, centimeters is probably going to be closer to what we're looking at. Next one, kilometer. Kilometers are a metric mile, but if you've ever driven in a foreign country, you've noticed that the number of kilometers you're going when you're going 60 miles an hour is a much larger number. That's because a kilometer is a shorter distance. So more than half a mile is a good way to think of a kilometer. It's really around 6/10 of a mile. And then finally, grams. Sometimes we'll use masses. And what does a gram feel like? Well, picture a dime. That's going to be a little bit more than a couple of grams. So cut a dime in half, make it a little bit smaller than that. You're probably pretty close to what a gram is. So the point is it's a fairly light measurement. So 1 dime would be a little bit more than a couple of grams. So be prepared to understand these on the test. So if I give you a measurement like how long is an unsharpened pencil, you'd be able to make a good estimate of what that would be. Now, yes, we have English units, which we use routinely in daily life, and metric units, which we use a little bit, and in science we use a lot. But eventually scientists realized that while the metric system had some advantages to the English system, there were still miscommunications that were happening. And in 1960, a group of scientists got together, once again in France, and they came up with SI units, which is the International System of Units. So why is it SI if it's the International System of Units? Well, in French, it's Systems International. Would be a loose translation. So that's why we call them SI units. And what they realized was, while it's great to have a meter and a lot of ways to use prefixes to change the meter, Sometimes that means there's confusion. You thought I was talking about inches and I was talking about meters, or you thought I was talking about centimeters and I was talking about decimeters. So what the SI group did was they came up with 7 fundamental ways of measuring things, which they called the SI fundamental base units. And they said if you're measuring in meters or length, you're going to use this. If you're measuring a mass, you're going to use this. If you're measuring a whatever, you're going to use this. So while it's convenient to have interchangeable base units with interchangeable prefixes, it still can lead to confusion. A good example of that was a satellite that was headed to Mars that literally went off course and became useless simply because at JPL out in California, when they were doing a course correction calculation, they calculated the amount of thrust in English units. So when they told the British scientists what thrust they had to use, they assumed that they were talking in SI units, and they assumed they were talking in newtons. But JPL scientists were actually talking in an older uh, type of thrust known as a foot-pound. So it leads to confusion. And if everybody was on the same page and said, okay, we're using SI units, and that would be newtons, that multi-million dollar satellite wouldn't have been turned useless. Now, one thing about measuring is really there's only 7 fundamental ways to measure things. Everything else is really these 7 or combinations of these 7. And what the SI team did was they came up with the 7 fundamental units that we're all going to use if we're in SI units. And then everything else is derived based on those fundamental units. So here would be the 7 fundamental units. Length is the meter, no surprise there. Mass is the kilogram. This is a commonly missed question, and I'm going to give you a hint here. There's going to be a question about what's the SI unit of mass on my test. There's going to be one on the final. And if you go on to take AP, it's going to be on the test on the final and AP as well. But still, students get it wrong because they think SI is metric, and it's not. Many scientists and business people felt the gram was too light for a lot of the masses they were measuring. So they lobbied for the SI unit of mass to be the kilogram, and it is. So SI unit of mass is not the gram, it's the kilogram. Time would be the second, which you're very familiar with. Temperature is Kelvin, which some of you may be familiar with, and we'll talk more about in this chapter. The mole, that's a type of measurement that we're going to use a lot in the second semester. So we're not going to use it now, but eventually we'll be talking about how we measure amounts of atoms and molecules, and that's the unit called a mole. Now the last two, electrical current and luminous intensity, both of those are important ideas in some situations, but they aren't things that we're going to see too much in first year chemistry. So the ampere and the candela, don't really worry about those two. Those are not fundamental units that I'm going to put on the test. So remember, the top 5 are the ones that you really should know and eventually be able to use. Now, how can everything else then be based upon those? Well, think about some common derived units that we use in chemistry. Sometimes we're talking about an area, which is really a length times a width. Well, if SI length has to be meters, then our unit would literally be a meter times a meter, which is a meter squared. So square meters would be our SI unit of area. Well, volume is a length, a width, and a height. Well, that's 3 lengths. That would be meters times meters times meters, or meters cubed. Now we get into something like density, which we're going to talk about this chapter. So density is one of the ones that we're going to do this calculation. So density is mass over volume. You're going to see and use that later in this chapter. Well, if mass is kilogram and volume we just said is meters cubed, that means the SI unit for density would have to be kilograms per meter cubed, which we're not going to see a whole lot in everyday chemistry class because that's really not a very convenient for us to use with some of the things that we're dealing with. We often use grams per milliliter rather than kilograms per meter cubed. But if I was reporting on the world market and had to report by SI units, I would use kilograms per meters cubed. Velocity, which we talk about the speeds of particles and the speeds of objects from time to time in chemistry, that's going to be a length divided by a time. Well, length is meters, time is second, so we get meters per second. Now, the last 3 down here, we are going to see and talk about and use throughout the course of the year. Force would be Newton, pressure would be Pascal, and energy would be Joule. But those are actually simplifications for what these things really stand for, which is way off here on the right. A Newton is a mass times a length over a square time. Well, that would be kilogram meters per second squared. That's a pretty big mouthful. So what we did was, to pay homage to Isaac Newton, we named the unit of force the Newton. And then a Pascal is basically a force per area, which would be newtons over meters squared. Well, that actually works out to kilograms over meters times second squared. Well, that's a mouthful as well, so we just call it the Pascal. And then finally, we're talking about energy. We're going to use the joule, which is actually a Newton meter, which is what it really stands for, shown over there. Now, do you need to know this stuff for the test? No. But you do need to know when we see newtons, we're talking about force. When we talk about pressure, we often measure in kilopascals and pascals. And when we're dealing with energy, we often talk about joules in chemistry. Now, the last thing that I really want to get into with this set of notes is scientific notation, which is something you've used before, so you should be familiar with, but I want to make sure we're all on the same page. Now, sometimes in chemistry, we use gigantic numbers or incredibly, incredibly small numbers, and those really aren't convenient to do math with. So we convert them into scientific notation to make the math and the reporting of those digits, and sometimes even the pronunciation of them, significantly, significantly easier. So remember, when we change a number to scientific notation, it's the exact same number. It's just reported in a different way. So something like 1,100,000. Well, that's not too big, but you're starting to get to be a lot of digits and a lot of zeros, and it's easy to confuse them. Well, we could convert that into scientific notation, right, as 1.1 times 10 to the 6th meters. So what are our rules when we're doing this conversion? Well, the first part is our coefficient. The coefficient, we say it has to be between 1 and 10. That's an easy way to pronounce it, but what it really is greater than or less than 1. I'm sorry, greater than or equal to 1 and less than 10. So typically we're looking at somewhere between 1 and 10. And then at the end, we have the exponent. And the exponent is literally telling us how we mathematically manipulate that coefficient. 10 to the 6th means we're going to multiply 1.1 times 10 6 times. And that's literally going to move the decimal 6 places to the right. And that then gives us our 1,100,000. Now the rules for our exponent is it has to be some integer. So it could be -1, -2, -3, 0, 1, 2, 3. It's going to be some integer. And remember one thing about negative integers. So if we have something like 2.3 times 10 to the 8th, well, 10 to the -8th, if you remember from math class, is really also the same thing as writing 1 over 10 to the 8th. So literally, 10 to the -8th means we're going to divide by 10 8 times. So if we have 2.3 times 10 to the -8th, that means we literally take 2.3, divide it by 10 8 times, and we get our original number here. So when we change really big and really small numbers, big numbers are going to give us positive exponents. Small numbers less than 1 are going to give us negative exponents. And the smaller they are, the more negative they become. The larger they are, the more positive they become. So, fundamental things about scientific notation. Remember, exponent is always some whole number. And remember, when the exponent is positive, we're actually multiplying by 10, so we're going to move the decimal to the right to get back to our standard notation number. And when the exponent is negative, that literally means divide by 10, which means we're going to end up moving the decimal to the left to move from our scientific notation number and coefficient back to its original standard notation number. So convert the following to standard notation. Now, 4.68 times 10 to the -1. 10 to the -1 means divide by 110. Well, that's going to give us 0.468. 4.73 times 10 to the -2, well, that means we're going to divide by 10 twice. That's going to move the decimal 2 to the left, and we're going to get 0.0473. And 4.7325 times 10 to the 3rd, that means we're multiplying positive integer. We're going to multiply by 10 3 times, and that's going to move our decimal 3 to the right, which gives us 4,732.5. Now, when you're converting to standard notation number to scientific notation number, first you're going to be finding where the decimal point really is. That's what you're doing. So moving the decimal to the right of the first non-zero digit. So if we have 125, then we're going to put it to the right of our first non-zero, which is going to be right there, and that would give us 1.25. And then what we have to do is figure out how many places we had to move that decimal to get to 1.25. And in this case, we had to move it twice. So if we had 1.25 and we wanted to get back to 125, we have to multiply by 10 twice. That's why it's a positive integer. So 125 is going to convert to 1.25 times 10 to the second. So if we have 123, what's between 1 and 10? Well, that's 1.23. And since we had to move it 2 decimal places, that means we got to multiply it twice by 10 to get back to 123. So remember, if it's a number greater than 1, we're always going to get a positive exponent. If it's a number less than 1, like 0.00006, well, first we have to change the number between 1 and 10. Well, that's going to be 6. And if we had 6, to get back to that number, 0.00006, we'd have to move the decimal 5 places. So we moved it to here. So to get back, we'd have to divide it by 10. 1, 2, 3, 4, 5 times. Hence, 6 times 10 to the negative fifth. And 1.02, or 1.002, 1002, that would be 1.002 times 10 to the third. Now, one of the things you need to be able to do with scientific notations, besides convert between scientific and regular and vice versa, is be able to plug this stuff in your calculator and do math with it, because you're going to use this technique a lot. So you need to be able to use your calculator to do calculations in scientific notation. So first, if I have 1.82 times 10 to the third, how do I put that on my calculator? Well, if you look closely at your calculator, so if you're doing this, pause and then go grab a calculator so you can plug it in and make sure you're doing the right thing. So now that you got your calculator, if I want 1.82 times 10 to the third, first I'm going to plug in 1.82. Now the times 10 part, you never, ever, ever, ever hit times 10. Your calculator has a way for meaning times 10, so you don't enter it. So what do you do for the times 10? Well, it's typically the EE key or the EXP key, which I mentioned down here at the bottom. For most of you, if you have a graphing calculator or a graphing style calculator, like the plain old TI-30X2, which many people have, you're going to find the EE key over on the left side, probably in the second row over, and it's going to be in the second spot. So it's going to be above a key. So you have to use the second function to get to it. So if you hit that EE key, now if you have an older calculator, you might get 2 zeros appearing to the left. If you have a graphing calculator, what's going to appear is 1.82, and then you'll all of a sudden see an E here. So with your graphing style calculator, when you hit the EXP key, instead of a couple zeros, and make sure you got your calculator out and you're trying this so that it makes sense to you, you're going to see a 1.82 and then that E will pop up. Remember, that means times 10. So it might look like this, or it might look like this. For most of you, it will show you the E. Now, since we want 10 to the third, then we want to put in 3. And when you hit 3, all of a sudden a 3 will appear right to the right of that E. Or in the case of the older style calculators, a 3 will appear in that second place. So that literally means to your calculator 1.82 times 10 to the third. Now when you turn it into paper, you can't put 1.82 E3. You need to put 1.82 times 10 to the third. Remember, E is just a convenient way for your calculator to show the times 10, so it doesn't have to do subscripts or superscripts anywhere on the display. So that's just an easy way to report it, but it's not how you can report it validly on a paper. So that's how you'd enter 1.82 times 10 to the third. 1.82, hit your EE key, which is probably a second function for most of you, over in the middle left-hand side of your calculator. An E will probably pop up, and then you hit 3. Now, if you have the multi-view TI calculator, which is great for doing fractions in math class, but terrible for chemistry, just be really careful. You're going to use the times 10 to the X or times 10 to the N key. Can't remember which it is. The problem with that calculator is you have to put things in parentheses very, very carefully, or it's not going to give you the right answer mathematically. With this style of calculator, it just clumps it all together. You don't need to worry about parentheses, which makes it 100% easier. Okay, now if you want to enter a negative exponent, you're basically going to do the same thing. You hit 1.73, so you enter your coefficient. Then you're going to hit your times 10 key, which on your calculator is EE for most of you. And that's going to probably make an E appear instead of the 2 zeros. So you'll probably get this appearing on your calculator display. Now, next you need to make it -6. Now, for older calculators, it wouldn't matter. You could hit 6 and then the plus minus key. For most of you that use a graphing calculator, it may matter. So you're going to hit the plus minus key first, and then you're going to enter 6. Now, this is not the subtraction key. Towards the bottom over on the right-hand side, you're going to see there's either a minus in parentheses, or a plus/minus key. And that's basically to make something negative. So you're going to hit negative, and that should appear as a negative to the right of the E, and then 6. And that literally means your calculator 1.73 times 10 to the -6. So that's how you would enter a negative exponent. Is you're going to, after you hit the EE key, which remember means times 10, so never hit times 10, you're going to hit the negative key and then whatever number, in this case is 6. Now, just to make sure that you can do this and it can work, I want you to do this math problem because this will show you if you're doing it wrong. And if you can't get this right, you need to come in and talk to me. 1.6 times 10 to the fourth. So you're going to put 1.6 EE and then the plus minus key and then 4. And if you're using the multi-view, you're going to have to put that all in parentheses, and you're going to have to move the parentheses over out of the exponent spot down into the regular area. And then you're going to hit divide. So divide by 3.05 times 10 to the 7th, which means you'll hit divide and then 3.05, your EE key, and then 7. When you hit equals, if you've plugged them in appropriately, no matter what calculator you're using, if you hit equals and plug them in appropriately, you should get a number that looks like this. Now, depending on how many displays decimal you have, you're going to get a slightly larger or slightly smaller number than this, but you should be able to get 5.2459 times 10 to the negative 12. So if you've plugged them in properly, you will get exactly this. And yes, I am positive this is exactly the right answer. So if you do not get this, that means you need to come in and get some help. So that ends our first set of notes over chapter 3.